So next part will be a very short explanation of gradient descent optimization algorithm. So there is a link right here. So I think that's a very nice blog. So let's take some time to go over some interesting concept of gradient descent optimization. Okay, so when we use neural network, we need to find the optimized weight, right? So when you there is always a basin when you perform gradient descent, right? We randomly find initial value in this basin. So it is not it usually okay. It should be a large MSE value. So we use a partial differentiation to help us to find the lower MSE value gradually, step by step. Okay, but usually there is only one global minimum MSE value. So basically, every gradient descent optimization algorithm should find the same data point. Should find the same lowest MSE value, right? But the answer is yes. Okay. But when we talk about optimizer, that means we want to find this lowest MSE value with a more efficient way. For example, if we need if some optimizer can find the lowest MSE value within, for example, 50 epoch, that means it only needs some certain partial differentiation to find the lowest MSE value, and that would be efficient. But some other optimizer, which is not, maybe that is not that good, so it need to take 100 epoch to find the lowest data point, lowest MSE point. So basically, they can find the lowest point, but they have different strategy. So for the optimizer, we want to find a more efficient optimizer to find the lowest MSE value. It is not necessary that if you choose two different optimizers and they give you two lowest data point. No, there's only one lowest MSE value. But with the same epoch or same step, maybe one of them can have a lowest MSE value when they both perform same amount of partial differentiation. So in this in this block, we're trying to find which is the most efficient optimizer so that we can use less steps to find the lowest MSE value. Okay, so the idea is that. So here it will introduce several optimizer, but we simply just go over it. Okay, we don't need to take we don't really need to dive into the mathematic things. Okay, so that is very interesting. That is the definition of gradient descent, right? We have theta. The new theta is the old theta and the minus the direction of your partial differentiation, right? And you have a learning rate which is eta right here. Okay, so basically that is the idea. But think about one thing is that the first idea this blog would like to introduce is the momentum. So take a look at this one. Okay, the left hand side is the gradient descent without momentum. That means when it goes to the lowest MSE value, and you can see that at the y axis you can see that is a zigzag, right? So sometimes the direction is to the larger y, sometimes the direction is to the smaller y. But from the perspective of x axis, you can see that it always goes to the right hand side, right? So with momentum means when you always go to the same direction when you do partial differentiation, if certain exit, they always go to some direction, you can increase a little bit when you perform, increase a little bit, we say steps, or the amount of value to the next theta. Okay, so that makes the entire gradient descent will become faster if you encounter such kind of situation that you always on certain exit you always goes to the same direction. So that's called momentum. Okay, so you can see that there's of course there are some values right here. So that is a vt minus 1 to vt. There is a gamma right here. So that means to try to evaluate the momentum of certain exit. Okay, so that is momentum. The next thing is called adaptive. So you can say that is called eta gradient descent, right? And that is called eta delta, right? So that is called what means adaptive? Eta means adaptive. That means adaptive. So adaptive means take a look at this one. You can see that the learning rate right here. There's another value, okay, right here. The GTII, okay, that is a little bit complex, but it means every time when you perform gradient descent, we imagine that at the first place, the learning rate should be large, so that you can search a very large area to figure out where is the lowest MSE value. But gradually, you should decrease your learning rate, because after a few epochs, your theta value will be in the basin, right, of the MSE basin, right? So the gradient will be smaller because it is a flat, right? It is become flat. So in the meantime, okay, you should change your learning rate to make it smaller than before. So you need this value. Okay, so of course there are some strategy to calculate this G value. Okay, in this case, after few epochs, your learning rate will become smaller, and that means you can find the lowest data point in a more fine-grained way. So that's called adaptive. So the eta gradient modify the general learning rate at each time step based on the past gradient. Okay, so that is the definition. So every time when you see ADA, that means adaptive. Okay, so we have two different strategies adapt such kind of strategy. So Adam, as we mentioned, we use Adam a lot, right? So what is Adam exactly? Adam right here, that is called adaptive momentum estimation. So it also has adaptive learning rate, but it also include the idea of momentum. So it has two different, it includes two different concepts. So it is relatively, it is a nice optimizer. It has adaptive learning rate. It has the concept of momentum. So I think it's, of course, there are some other optimizers, but we don't use them quite often. So I I think it's very nice to take a look at this figure. Okay, that is a very nice one. So let's take a look at the left hand side. So firstly, we take a look at the red one, which is the stochastic gradient descent. So that is the figure of the MSE, right? And you can see they randomly start from the starting point, and take a look at the red one, and you can see that the red one will slowly goes to the lowest data point, which is marked as star, right? But you can see that it seems like it is slow, right? That is because the original gradient descent does not contain the concept of adaptive learning rate. So at the first beginning, it is slow, and at the middle of the training, it is slow as well, and at the end, it is still slow. If you choose a very bad learning rate, it will eventually goes to the somewhere near the stop mark, but it is slow. That is the reason why we still need adaptive learning rate. Okay, let's take a look at the green one. That is the momentum. So you can see that at the starting point, it is somewhere on the middle of the hill, the mountain, right? Somewhere here, and it goes to the lower point, and you can see that with the momentum, it tries to climb up to some other hills, right? At the wrong place. That is because the momentum. Sometimes because the momentum. Sometimes because it keeps the momentum, so it will goes to some wrong places. But as you can see that after it climbs, okay, take a look, the green one at the mountain to the other mountain and go back to the basin, right? It eventually will go back to some place because the momentum stops at the other side right here and go back to the basin. Okay, and as you can see that it goes too much right here. It passed the star point, star point, right? Because of momentum. So momentum is not that still not that good. So let's take a look at the AD grade. Okay, the blue one. Okay, and you can see because of the momentum, so the blue dots goes to the other basin, and then go to the start point. It is fast because it has adaptive learning rate, so it can it can go to the lowest point more faster than SGD. So it's quite worthy to take some time to take a look at this figure. Okay, so that is okay. We will not go over the entire thing because there are too many mathematics things. The only thing is likely to show you how how different optimizer works. But as I mentioned, usually we only use some optimizers like add-on when we implement our system. Okay. So that is the things I would like to introduce, and that is the class of this week. Okay, we stop right here, and next week we will talk about language model, which is a very important topic.